Now we are going to deal with recurrence relations. So first of all, we will deal with the definition, how we will define the recurrence relation. So for a sequence of numbers, for a sequence of numbers, or numeric function, or numeric function, that is a naught, a1, a2, up to ar. An equation relating ar for any r, an equation relating ar for any r to one or more of the ais, to one or more of ais of the ais where I is less than r, okay, where I is less than r is called recurrence relation. Definition is very simple, is called recurrence relation. For example, ar equals to 4 times a r minus 1 and r is greater than equals to 1, or ar equals to ar minus 1 and minus 2 times a r minus 2 where r is greater than equals to 2 are recurrence relations. So recurrence relations are very simple equations by which we relate the terms of any sequence in respect or in terms of the other, or in respect to the other terms of the sequence. So here we will define the order of recurrence relation and degree of the recurrence relation. So what do we mean by the order of the recurrence relation? Order of the recurrence relation, the difference between the highest and the lowest subscripts. The difference between lower and higher subscripts of AI or AR or f of x, it may be of the type of x, or y of n is called order of the recurrence relation. Order of the recurrence relation. Okay. For example, 13 AR and plus 12 AR minus 1 equals to 0 is of order 1. Is of order 1. Because the lowest subscript is R minus 1 and the highest subscript is R, and their difference is, that is, R minus R minus 1 equals to 1. Okay, which is the order of this different order of this recurrence relation, and it is also called a differential equation. Okay. Another example we can consider here, like at f of x plus 2 times f of x plus 1 and plus f of x plus 2 equals to k of x. So here the higher subscript is x plus 2 and the lower subscript is x, then their difference is 2. Okay, then their difference is 2. Then the order of this recurrence relation is 2. Now we will move to the degree. Okay, degree of a recurrence relation. The highest power of AR, the highest power of AR or f of x or y of n is called the degree of recurrence relation. Very simple. For example, AK equals to k times AK minus 1 whole square for all k is greater than equals to 1 and a naught equals to 1. So here the power of the AK is 1. Therefore, the degree of this recurrence relation is 1. Okay. Now we consider the another example, like yk plus 2 square and then plus 2 times yk plus 1 square and minus yk equals to 0. Then the degree of this recurrence relation is nothing but 2. Okay. Okay. Okay, if it is 3, then the degree of this recurrence relation will be 3. And now we are going to deal with another example, that is AR to the power 4 and plus 2 times AR minus 1 to the power 3 and then plus 3 times AR minus 2 to the power 2, then plus 4 times AR minus 1 equals to 0. So what about the degree of this recurrence relation? The degree of this recurrence relation is nothing but the 4, because the power of AR to the power a r to the highest power is 4. Okay. Now find the first four terms of. Next, we deal the another example. For example, find the first four terms of first four terms of a k equals to k times a k minus 1 whole square for all k is greater than equals to 1 and n not equals to 1. So the relation is very simple. A naught is given that is equals to 1. What about A1? If you put 1 in place of k here, so A1 equals to 1 into A1 minus 1 square. That is 1 into, or there is no need to write the 1. 1 minus 1, that is A naught square. So A1 equals to, what is the value of A naught? That is 1. 1 square equals to 1. Okay. And what about A2? A2 is nothing but 2 times A2 minus 1 square. That is 2 into A1 square. That is 2. Okay. What about A3? A3 is nothing but 3 into A3 minus 1 square. That is 3 into A2 square. That is 3 into 4 equals to 12. So here are the three terms. Now we can find out the another more terms for this um, example. Okay. Now we deal with another example. Show that the sequence show that the sequence 2, 3, 4, 5, 2 plus n for n is greater than equals to 0 satisfy the recurrence relation. Satisfy the recurrence relation. Okay. That is a n equals to 2 times a n minus 1 and minus a n minus 2 n is greater than equals to 2. Okay. So if we see for n equals to 1, that is a1 equals to 2 times a naught, and we see here a n equals to, what about this, a n equals to the nth term of the sequence is 2 plus n. So a n minus 1 equals to n minus 1 will be, we put here n minus 1 in place of n, okay, then 2 plus n minus 1. What about it? It is n plus 1. Okay, n plus 1. So what about a n minus 2? N minus 2, n minus 2 will be 2 plus n minus 2. That is equals to n. Okay, now we cross it. Now 2 times a n minus 1 n minus a n minus 2 will be equals to 2 times n minus 1. What is the value of n minus 1? That is n plus 1. And minus n minus 2, that is n, which is equals to n plus 2. Is equals to n plus 2. And which is nothing but a n. Okay, hence satisfied. Okay, which is the proof of the above relation. So now we move further and we classify the all the recursive relation, recurrence relations based on their degree and order. So now we talk about the linear recurrence relation with constant coefficients. Linear recurrence relations with constant coefficients. Okay. So if the degree of the recurrence relation is 1, then the recurrence relation is called the linear recurrence relation. Okay. If the degree is 1, then the recurrence relation is called linear recurrence relation. And generally it is of the form C naught an plus C1 an minus 1 plus C2 an minus 2 and then plus dot 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 plus ck a n minus k equals to f of n, where ci where ci I is greater than equals to 0, less than equals to k, where ci is constant and fn is a function which satisfies the equation, is called a linear recurrence relation. If fn is equals to 0, okay, if here fn is equals to 0, that is the above recurrence relation is in the form c naught n plus c1 n minus 1 and plus dot 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 plus ck a n minus k equals to, then it is said to be the homogeneous. Okay, then the recurrence relation is linear homogeneous recurrence relation. If it is non-equals to 0, okay, if it is equals to 0, then it is said to be linear homogeneous recurrence relation. And if it is not equals to 0, if fn is not equals to 0, then it is said to be non homogeneous linear recurrence relations. Okay, non homogeneous recurrence relation. Now, for example, okay, it is better to write here non homogeneous recurrence relations. Okay, now for example, here we consider some example like a n equals to 5 times a n minus 1 is a homogeneous linear recurrence relation. Okay, is a linear homogeneous recurrence relation. Okay, why? Because it can be written as n minus 5 times of n minus 1 equals to 0. And another one example here we are going to do, that is a n n equals to 2 times a n minus 1 or n minus 2 is not a linear homogeneous relation with constant coefficient. A term such that n minus 1 are not permitted. These terms are not permitted. Okay. The multiplication of two consecutive terms are not permitted. So it is said to be non-homogeneous recurrence relation with constant. It is not a linear homogeneous relation. It is not a linear, okay? Not a linear homogeneous equation. Not a linear homogeneous recurrence relation. Okay. Now, if we talk about the another a n minus 2 times a n minus 1 equals to pi is non-homogeneous linear recurrence relations. Okay. Now, what do you mean by the solutions? What do you mean by the solution of a recurrence relation? How we will find out the solution of a recurrence relations? Now, solution of recurrence relations. So these are very similar to the differential equations. Okay, an explicit formula which satisfies the recurrence relation with initial condition is called a solution to the recurrence relation. The three methods of solving recurrence relation are discussed. Number one, iteration method. Second, characteristics roots method. Characteristics root method. And third one is using generating function. Using generating functions. For example, if we talk about the iteration method, okay, first of all, we talk about the iteration method. So, how we will define the iteration method. As the name suggests, in this method, the recurrence relation for n is used repeatedly to solve a general expression for n in terms of n. Okay. Repeatedly using for n is used repeatedly to solve a general expression for n in terms of n. For example, Solve the recurrence relation. Solve the recurrence relation, that is ak equals to 2 times ak minus 1. A naught equals to 1. Solution, given ak equals to 2 times ak minus 1. Okay. Now, what about ak minus 1? Ak minus 1 can be written as 2 times into 2 times ak minus 2. And it can be written as 2 times into 2 times into 2 times ak minus 3. Okay. And similarly, it will go up to ak equals to 2 to the power 3 a k minus 3. Okay, it can be written as like this. So you can write it in terms of a naught, that is a to the power k is equals to 2 to the power k a naught. Okay, 2 to the power k a naught. And what about the value of a naught? A naught is equals to 1. Then this implies that a to the a k equals to 2 to the power k, which is the solution for all k is greater than equals to 1, which is the solution of the given recurrence relations. Now we discuss another one example in the support. Solve the recurrence relation. Solve the recurrence relation an equals to n minus 1 n plus 1, subject to initial condition a a1 equals to 4. A1 equals to 4. Okay. The solution, given a k equals to a k or n my a n, you can write it here in the form of n. Okay, n equals to n minus 1 plus n. So similarly, it will be written as n minus 2, then plus n minus 1, and then plus n. Okay, and n minus 3 plus n minus 2, n minus 1 plus n. And similarly, it will be written as n minus k, n minus k plus n minus 1, n minus 2, and plus 2 plus n minus k minus 1. Okay, n minus k minus 1. And it will go up to the desired terms. Okay. So now replacing, if we talk about the terms now, if we want to hear A1, okay, we know the value of A0 or A1. I think we know the value of a1. So we want here 1. How we will get the 1? Obviously, if you put in place of k, if you put here in place of k, that is n minus 1. Okay, then we will get the 1 here. So a1 and then plus in place of k, okay, in place of k, n minus 1. Then plus n minus 1 plus n minus 2 plus dot 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 plus. So in place of k n minus 1, that is n minus 2, n minus 2, and it will be plus 2, okay, plus 2. So it can be written as a1 minus 1 or plus 1 plus 2 plus 2 2 2 2 2 plus n. So it will be a1 minus 1 and sum of first and natural numbers. Okay, sum of first and natural numbers. Okay, that is n minus 1 by 2 and n minus 1 by 2. Okay, so after solving this, we know the value of a1. a1 is equals to 4. So a1 minus 1 equals to 3. 3 plus n minus 1 divided by 2, which is the required solutions. Okay, which is a required solution. Now we move to the another example. So the example are very simple. If you try yourself, then you can find out the solution very easily. Solve a n equals to n minus 1, given a naught equals to 5. Okay, solutions. Given an equals to n minus 1. Okay, then it will be n minus 1 a n minus 2 and n minus 1 n minus 2 n minus 3. Okay, n minus 3, and then it will go up to n minus 1 n minus 2 n minus k a n minus k minus 1. Okay, and k minus 1. Now, in the like the previous question, if we put here, because we know the value initial condition of a naught, so in place of k, if we put here um, n, I think it should be uh, n minus 1. Okay, in place of k, put k equals to n minus 1. Then n will be n minus 1 or up to 1 into a, and which is nothing but a naught, which is nothing but, okay, it should be plus 1. Okay, a naught. So it is n factorial. What about the value of a naught? That is 5. So a n equals to 5 times n factorial, which is the required solution. So here are the number of questions to solve uh, these difference equations or recurrence relations. Okay, so here we are going to deal with another method. So before going to the to move to the another method, we I am going to arise here two questions, or which is for your practice, which are for your practice. Now, question number one: find the recurrence relation for the closed form. Okay, there is no need to solve this. It's a very much better question. Solve the recurrence relations. Solve the recurrence solve the recurrence relation a n equals to 2 times n minus 1 and plus 1. That is a1 equals to 7. Where a1 equals to 7. So how we will solve it? If we if we try to solve, okay, we take only 2 minutes here. So 2 times and 2 times a n minus 2 plus 1. Okay, that will be how much? 2 to the power 2 n minus 2 then plus 2. Now again we put here 2 to the power 2, and in place of n minus 2, in place of n minus 2, we will write here 2 times n minus 3 plus 1. 2 times a n minus 3, then plus 1, and plus 2, then plus 1. Okay. So it will be 2 to the power 3 a n minus 3 and plus 2 square plus 2 and plus 1. So similarly, it will go up to k, that is a to the power n equals to 2 to the power k, a to the power n minus k plus 2 to the power k minus 1 plus 2 to the power k and plus dot plus 1. Okay. So if you put here k equals to n minus 1, put here k equals to n minus 1. So a n equals to 2 to the power n minus 1 and a n minus n minus 1 and plus 1 plus 2 plus dot plus 2 to the power k. In place of k, we can write here n minus 1. So what about it? 2 to the power n minus 1, n and n cancel out, that is a1, and the sum of the geometric series with common ratio 1. Okay, of the nth term geometric series with common ratio, I think it's 2. Okay, so 1 into 2 to the power k minus 1, 2 to the power n minus 1, and then minus 1 divided by 2 minus 1. Okay, that is equals to 7, because the value of a1 is given in the above question 7, 2 to the power n minus 1, and then plus 2 to the power n minus 1 and minus 1, which is nothing but the 8 into 2 to the power n minus 1 n minus 1. And 8 can be written as 2 to the power 3, 2 into n minus 1, n minus 1, which is nothing but 2 to the power n plus 2 minus 1, which is the final solution, required solution of the recurrence relations with the help of iteration method. Next, we move the another method, which is method of characteristics rules. Okay, and it's really an awesome method. It takes the time to solve the problems. So here we can go with this method too. So method of characteristics root. So it's the second method. It is the second. Okay. So if we have the homogeneous recurrence relation with constant coefficients, that is an plus c1, an minus 1, and plus c2, n minus 2, and plus 2, 2, 2 plus ck, an minus k equals to 0. Homogeneous recurrence relation with constant coefficients. So in this case, we can find out the solutions of this recurrence relations, this type of recurrence relation, in terms of the roots of the characteristics roots.